A sliver of a residential tower cuts up through city haze, stacked floor on floor, balanced on a plot barely wider than a lane. The constraint isn't just height. Wind can lock onto a narrow frame, set up rhythmic forces, and nudge the whole structure off-plumb, while the ground below has to take every pull and push without settling. So engineers fight back with thick shear walls, outrigger trusses, and even floors that deliberately let air pass through. Ideas refined through wind tunnel thinking and field monitoring. Because if one pour drifts or one connection lands slightly wrong, the vertical rhythm turns into rework, cost, and comfort problems that follow the building all the way up. And in this build, we'll decode the exact structural trick in the sequence that makes it buildable, that turns a needle-thin outline into a stable, livable tower. Cold open, scale plus constraint. From the street, it reads like a line drawn against the sky, too narrow to be forgiving, too tall to be casual. This kind of slender high-rise pushes stiffness to the edge. Crosswinds don't just push. They wrap around corners, shed into swirling patterns, and load the tower in pulses, a phenomenon engineers call vortex shedding, where rotating air wakes can drive side-to-side motion over and over again. You can't just add more bulk. On a tight footprint, mass is expensive, space is precious, and every added ton increases demands on the foundation. Instead, the strategy becomes redirection and relief. Shape the structure to resist, and shape the air to behave. Later, the make-or-break move is how the hidden spine is tied into the outer walls, so the whole needle responds as one unit, not as parts arguing with each other. To see why that matters, the mission and stakes come first. The mission is simple to describe and difficult to execute. Stack a small number of ultra-high-end homes high above Manhattan to capture light, views, and proximity to the park corridor that has become a magnet for this kind of development. The stakeholders are equally straightforward. Builders and engineers have to deliver a structure that is safe and predictable in wind. Future residents expect quiet elevators, doors that don't rack, windows that don't groan, and a top-floor experience that feels solid even when storms roll through. And then there's the city itself, managing street protection, construction impacts, and the long-term effects of extremely tall, extremely slender forms rising from tight blocks. The first stake is technical, keeping lateral drift and, more importantly, acceleration within comfort limits in a profile this thin. Even when a tower is structurally safe, motion can still be noticeable. The second stake is schedule and cost. With minimal laydown space and tight tolerances, a single error can ripple. Missed deliveries, out-of-sequence work, and financial pressure that compounds as time slips. So what lets a tower like this stay comfortable without simply hanging a giant counterweight at the top? The answer starts at the block itself. The site behaves like a constraint box. The footprint is compact, squeezed between neighboring structures, which means there's little room to stage materials, swing large equipment, or store components for later. It also has to thread construction through and around a preserved historic base. Steinway Hall, a building from 1925 associated with architects Warren and Wetmore. That preservation requirement changes sequencing. Demolition, drilling, and heavy vibration work can't be allowed to damage what must remain. At street level, the city environment dictates the workday. Noise limits, pedestrian protection, and controlled access determine when crews can cut, drill, pour, and lift. And because the structure is so slender, teams don't eyeball plumbness. They climb survey control points up the building, constantly rechecking line and level, watching for any drift that could multiply as floors stack. If they misread ground conditions or movement, if settlement begins or the core starts growing out of plumb, those defects can lock in. Later trades inherit the misalignment. Facade panels fight the structure, elevators fight the shaft, and corrections get harder the higher you go. So how do you anchor a needle to bedrock when you barely have space to drill? The design logic explains why the structure is drawn the way it is. Design logic, the system diagram in words. Think of the tower as a set of interlocking systems built to share load. First, the structure. At its center is a reinforced concrete core, its spine, with shear walls that are extremely thick near the base and taper as the building rises. In this project, those walls are reported at roughly 30 to 36 inches thick down low, thinning to about 16 inches higher up. That spine provides most of the stiffness. The outer walls and columns carry gravity loads and also feel wind pressure and suction at the facade. Third, the link between them, outrigger trusses. Their purpose is to tie the core to the perimeter so the whole cross-section resists overturning together. The constraint is precision. If an outrigger lands even slightly off, it can introduce unintended stress and distortion. The consequence is cascading. Misalignment at the interface can propagate into floors, facade joints, and long-term movement. Fourth, the envelope. The facade must transfer wind forces back into the structure without racking or leaking, while staying straight enough for tight seals and consistent sightlines. Fifth, MEP and controls. In a narrow core, power, water, fire systems, and communications are packed tightly, and some equipment levels double as aerodynamic relief, openings that let wind pass through to disrupt vortex shedding. The governing principle is stiffness and damping through wall thickness, high-strength concrete, reported as 14,000 pounds per square inch in the shear walls, and wind-permeable mechanical floors. But none of that works until the site itself is made buildable. Before the tower rises, the project has to create its own access, inside a building that can't be treated like a blank slate. Within the preserved base, crews carve out protected corridors and staging zones. The purpose is twofold: shield heritage, finishes, and structure, and still create a working route for materials, tools, and waste. The constraint is space. There's no expansive yard for rebar cages, no wide apron for stockpiled panels, so the solution is to convert the street edge into a controlled interface. Protection canopies for pedestrians, managed entry points, and hoists that turn vertical space into a supply line. Material flow becomes choreography. Deliveries are timed close to installation because holding inventory on site would clog the base and slow everything else. The bottleneck is predictable: curbside congestion and limited hoist capacity. The mitigation is equally practical: strict delivery windows and sequenced lifts so the right materials arrive when the right crew is ready, not earlier. Once access exists, the next dependency is obvious. The tower has to be stitched to the ground strongly enough to resist wind overturning. Foundation/anchoring/ground improvement. A slender tower doesn't just press downward. In strong winds, overturning tries to lift portions of the foundation, like prying up one edge of a base plate. So the foundation strategy relies on anchoring into bedrock. In this build, engineers reportedly drilled nearly 200 steel anchors, some extending as deep as about 100 feet into Manhattan bedrock. The purpose is hold-down capacity, resisting uplift so the mat and core stay clamped to rock when wind loads reverse. The constraint is proving it works. An anchor is only as good as its bond to rock and grout, so acceptance depends on load testing and instrumentation. Proof pulls that confirm each anchor meets the design pull-out requirement before it is fully integrated into the foundation system. The risk scenario is ugly. If anchors slip or the base settles unevenly, high-strength walls can crack, and a slender tower can amplify the consequences through alignment and serviceability issues. The mitigation is conservative detailing, adequate bond length, controlled grouting, and test and verify discipline before the structure is allowed to climb. And with such a tight footprint, the work has to rotate through a few access points: drill, case, grout, test, then move the rig without damaging the preserved base. Once anchors are accepted, the base slab and starter walls tie everything into a single diaphragm. Then the vertical rhythm begins. Core build sequence: vertical/linear/planar. Once the foundation is ready, the project becomes a repeating cycle: fast, precise, and unforgiving. It starts with set-out. Survey control points climb upward with the structure, giving crews reference lines for core walls, openings, and perimeter edges each time a new lift begins. Then comes reinforcement. In thick shear walls, rebar is dense, embeds are numerous, and sleeves for future systems have to land exactly where the next trades expect them. The purpose is strength and continuity. The constraint is congestion. Too much steel in too small a space can make concrete placement difficult and increase the risk of voids. Next is the pour. The tower's core uses ultra-high-strength concrete, reported at around 14,000 pounds per square inch for the shear walls. High-strength mixes bring their own challenge. Heat of hydration and curing behavior have to be managed so the concrete gains strength without uncontrolled thermal cracking. Crews plan placements, consolidate carefully, and protect curing conditions. After curing, forms are stripped and the structure is checked. Surveyors verify plumbness with high-precision instruments, and if readings drift, crews make micro-corrections on the next cycle. Small adjustments before the next lift locks alignment into place. Those tolerances matter more here than on a broader tower. In a slender profile, small deviations compound. Enough drift and the facade system starts fighting for fit. Elevator rails demand shimming, door frames and partitions inherit the skew. Tempo is protected by parallel work. While the core climbs, other crews frame and deck adjacent areas, and logistics stays synchronized so the site doesn't stall, waiting for a single bottleneck lift. Then the rhythm breaks at special levels designed for the wind. At multiple tiers reported at the 51st, 71st, and 86th floors, sections are intentionally left open so air can pass through. That changes everything. Formwork, edge protection, MEP routing, and facade detailing all shift to accommodate openings that are aerodynamic tools as much as architectural features. If alignment is everything, the next question is the critical one. How do they connect the core to the outer walls without introducing stress? That connection is the signature operation. Signature operation, the impossible moment. The high-risk moment isn't a single dramatic pour. It's when the building stops behaving like a core plus perimeter and starts behaving like one frame. That's the job of the outrigger trusses. First, crews pre-assemble outrigger components in pieces sized for the site's limited lifting and staging capacity. The purpose is to reduce time spent fitting heavy components in the air. Then the lift. Pieces are hoisted into position at designated levels where the core and perimeter lines are designed to meet structurally. Temporary supports take the weight and hold geometry while the team checks everything. This is where control systems matter. Survey targets are read live. Measurements are compared to allowable tolerances. And there are hold points, moments when work must stop until alignment is confirmed. Only after geometry is verified do crews make the connections permanent, welding and bolting steel where required, and casting or grouting interfaces so the load path becomes continuous. The catch is that once those links are locked, forces redistribute immediately. The perimeter starts sharing overturning and drift control with the core, so the team watches for unexpected movement, using monitoring to confirm the structure is behaving as predicted. And there's a contingency plan. If readings drift beyond limits, the operation pauses. The lift can be set back onto temporary stools, connections can be undone, and the assembly can be reset rather than forcing a misfit into the building. After outriggers, the tower can resist wind as a unified system, but now another problem threatens progress. Feeding this vertical machine on a block with almost no space. On a site like this, logistics is not background work. It's a structural dependency. High-strength concrete is especially timing sensitive. Batching, transport, and placement have to align so the mix arrives workable and performs as designed. That means crews must be ready to place immediately when trucks arrive, because there's little buffer in time or space. For other materials, the approach is to reduce what can't be handled easily. Large elements are avoided where possible, or broken into smaller pieces that can navigate urban routes and fit the hoists. Inventory strategy leans heavily toward just-in-time delivery. The benefit is a clear sight and faster movement through the preserved base. The trade-off is exposure. A delayed truck or a missed delivery window can idle crews and disrupt the pour schedule. Facade units and interior packages are sequenced to match the climb. The goal is to reduce double handling, no hauling materials up, storing them in corridors, then moving them again through a narrow core. But flow means nothing without proof. So the next gate is verification. How every pour, joint, and alignment is checked before the building is allowed to keep rising. Safety, quality, and verification. Gates in a slender tower, quality control is what keeps small defects from becoming permanent behavior. Concrete is verified continuously. Samples are taken, cured, and tested to confirm strength gain matches what the design requires. Structural monitoring tracks whether the building's response is consistent with expectations as loads accumulate. At critical steel and embed interfaces, especially around outrigger connections, inspection goes beyond a quick look. Visual checks confirm fit-up, and non-destructive testing is used at key joints to catch hidden flaws before they are buried behind finishes. Alignment is treated as a deliverable. Floor-by-floor survey reports document plumbness, and deviations trigger corrective actions before the next lift proceeds. Traceability matters because responsibility matters. Batches, lots, and sign-offs tie each pour and connection to specific crews, inspectors, and approvals. A common defect pathway in thick walls is incomplete consolidation, honeycombing or voids. Testing and inspection can reveal those weaknesses early and repairs happen before the structure is asked to carry increased loads. Once the skeleton is verified, the building still isn't livable. It has to become an operating system. Power, water, life safety, and controls inside a core that can't get any wider. Systems integration, NIMEP/controls/operations. A tower like this is a machine for living, and its systems have to fit inside a narrow spine. Power, water, fire protection, drainage, and communications stack vertically through tight shafts. The purpose is redundancy and reliability. The constraint is space. Routing conflicts are harder to resolve when there's no extra chase to steal from. Some equipment and levels do double duty. They house mechanical systems, but they can also function as aerodynamic relief, open sections that let wind pass through, reducing organized wind forces that drive sway. Life safety redundancy is designed into the vertical stack. Backup power for critical functions, multiple risers for fire protection, and isolation valves that can contain an incident to a limited zone rather than disabling the whole building. Even with all the stiffness strategies, thick shear walls, high-strength concrete, outriggers, and openings, motion doesn't vanish. Reports describe that top levels can still move by several feet during storms. Structurally, that can be acceptable. For comfort, the engineering focus shifts to tuning, ensuring systems, partitions, and facade details tolerate movement without noise, leaks, or damage. Commissioning becomes the mindset: test, tune, retest, until pumps start on command, alarms communicate correctly, elevators behave smoothly, and ventilation responds under fault conditions. And then comes proof under real conditions, phase testing, early occupancy, and the first seasons of wind. Commissioning, testing, and first run. The final proof doesn't happen in a rendering. It happens in stage testing. Commissioning steps from components to subsystems to full building drills, fire alarms, pumps, elevator operations, pressure zones, and integrated responses are tested together before residents move in. During early operation, instrumentation watches how the structure and systems behave, especially during storms. So engineers can confirm the real tower matches the models and assumptions that guided the design. By 2021, the tower was reported complete after years of construction. Yet later reporting described low residency well after opening, with the building characterized as largely empty by 2023. Engineering can deliver stability, safety, and performance. It can't decide who shows up. The structure stands while the city keeps debating what should fill towers like this.